This is Chemical Processes for Micro and Nano Fabrication, Lecture 15, Diffusion, Part 3, our last part in our series on diffusion. I'm Chris Mack, your instructor for this class, and our reading for this series of lectures on diffusion is Chapter 3 of our textbook by Campbell. So, last time we talked about analytic solutions to the diffusion equation where we made the assumption that the diffusivity was constant. If we want to go beyond that simplifying assumption, we need to worry about the mechanism of diffusion a little bit more carefully. And the mechanism of diffusion depends on the kind of impurity that we're dealing with. One kind of impurity is called interstitial impurities. These are impurities that are not a part of the crystal lattice. Stitial means built-in, and interstitial is between the built-in lattice sites. Now, interstitial impurities are not dopants. They're not activated. They don't act as dopants, either acceptors or donors. But other kinds of materials can act as impurities and diffuse around. And we sometimes worry about how copper or iron or gold might diffuse in our semiconductor. And if they're interstitial, the answer is they diffuse very quickly. And this is one of the big problems with these metal contaminants like the transition elements. They diffuse very quickly because they're not bound into the crystal lattice site. Dopants, on the other hand, are substitutional impurities. Atoms that occupy a lattice position in the silicon lattice, that is, that they replaced a silicon atom. Here the diffusion is going to be quite slow because in order to get that atom to move, bonds have to be broken. So that's the key thing we're going to look at here is what it takes to get one of these atoms to move from one lattice site to another lattice site, and what kind of energy is required to get it to move. These substitutional impurities can have, in and of themselves, several different mechanisms for moving. The simplest, the one we would probably think of first, is a direct exchange. So I've got a silicon atom here, I've got a dopant atom here, and they're both built into the lattice structure, and they simply swap places. To do that, though, maybe the bond between those two atoms is not broken, but many other bonds have to be broken. 6 or 7 bonds must be broken in order to get that exchange to occur. Well, that's a lot of energy. And if it takes a lot of energy, it happens slowly. There's another way, however, that a dopant can move, and that has to do with the possibility of vacancies. Now, a vacancy is a position in the crystal lattice that should hold a silicon atom, but in fact is empty. And that happens. No crystal is perfect. There will be certain defects, including these vacancies. And at high temperatures, the number of these vacancies, the concentration of vacancies, is greater. In fact, at very high temperatures, it can be a very large number of vacancies. So the probability that there's going to be a vacancy next to the dopant atom is much higher at these high temperatures. Now think about a vacancy, an open spot, right next to a dopant atom. To get that dopant atom to move into that spot, well, only 3 bonds have to be broken. That's a much lower energy requirement, therefore it's much more likely to happen, therefore it's faster. So vacancy exchange turns out to be one of the dominant methods of getting dopants to move around within the crystal lattice. And we simply have to worry about the concentration of these vacancies. All right, well, maybe I misspoke. We don't simply have to worry about that because there are different kinds of vacancies. Vacancies is a spot where I should have 4 bonds attaching to a silicon, but the silicon's not there. So what do I have? I have 4 dangling bonds. Dangling bonds are very easily ionized. Either the electrons move away and the vacancy becomes positively charged, or another electron falls into that spot to put 2 electrons where that bond would go, and that makes the vacancy negatively charged. Now there's 4 spots, so it's possible to even have charged -4 or charged +4, and anything between 1 and 4. So it's quite frequent that these vacancies are charged. Now, how is that going to affect the probability that a vacancy swaps with a dopant atom? Well, our dopants are charged as well. Our donors are ionized by donating an electron. Our acceptors are ionized by accepting an electron. So the dopant atom ionized is going to be charged. Now, if I've got a charged dopant atom next to a charged vacancy, will that affect the probability of a vacancy exchange? Well, sure. If they're the opposite charge, it's much more likely that the dopant atom will move into that vacant spot, pushing the vacancy off to the other side. If they're the same charge, well, then they repel each other, and it's much less likely that you'll get a vacancy exchange. Well, that makes things quite a bit more complicated, because now we not just worry about the number of vacancies, we worry about the number of vacancies that are charged +1, the number of vacancies that are charged -2, etc. So how do we take that into account? Let's consider as an example an N-type ionized donor atom. So it's positively charged. There, if there's a positively charged vacancy, it's basically going to ignore it. It's not going to exchange with it. But if there's a negatively charged vacancy, then it will be drawn into that vacancy. So we're going to let D- be the diffusivity into a negatively charged vacancy. What we'll say is that the overall diffusivity, the thing we're looking for overall, is this D- constant multiplied by the probability that that particular vacancy is negatively charged. If it's a very low probability, then it's not going to have much chance. Even if D- is high, we're not going to have much chance of that diffusion occurring. But if there's a high probability that the vacancy is negatively charged, well, then this is going to be a mechanism of diffusion. So what is the probability that a vacancy is negatively charged? Well, that depends on the number of free electrons moving around. The larger the number of free electrons, the more likely it is one of these vacancies is going to capture it. So we say the probability the vacancy is negatively charged is proportional to the ratio of N, the concentration of free electrons, divided by Ni, the concentration of free electrons in an intrinsic material. So that ratio tells us something about the likelihood that the vacancy is going to be negatively charged. So the overall diffusivity will be this rate constant D- multiplied by N over Ni. Well, as I said, there can be more than just one negative charge vacancy. We might have neutral vacancies. We might have doubly negative vacancies. When we include all the possibilities, we get something like this. Here's the overall diffusivity. It's equal to the diffusivity into neutral vacancies, that's this D0, plus the diffusivities into a one negatively charged vacancy multiplied by N over Ni, probability that we'll find a negatively charged vacancy, plus D-, this is the diffusivity into a doubly negative vacancy, a vacancy that has two negative charges, multiplied by N over Ni squared. And 3 would be N over Ni cubed, etc. This is how we combine all of these terms together and see what the final diffusivity will be. Well, for an N-type material, we know that the number of mobile electrons is about equal to the number of dopant atoms, the donor atoms that we've added. Therefore, what we found from the previous equation, diffusivity is a function of N, we see that diffusivity is going to be a function of the concentration of the dopant. And the higher the concentration of the dopant, the more likely the vacancies are charged, in such a way to attract an ionized donor, and therefore we get higher diffusivity with higher doping levels. The same is going to be true for positively charged vacancies in a p-type material. But basically positively charged vacancies in an n-type material don't help us, don't enhance diffusion at all. They don't participate in the diffusivity at all. And in fact, they're not very likely. If we have a lot of negative charges floating around, it's very unlikely that you'll find a positively charged vacancy. Now, the exception to that is when you're near the junction. When you're near the junction, N and P are about equal to Ni, and you could have both positively and negatively charged vacancies hanging around, and they both can affect diffusivity. And then, in that case, we take everything into account. There are other mechanisms for diffusivity as well. I hope you're getting the feeling now that the diffusivity of a dopant in silicon is a little bit complicated. It's going to get more complicated by the time we're done. Another issue we worry about is called transient enhanced diffusion, or TED. Remember, and again, we haven't talked about ion implantation yet. That's going to be the subject, in fact, of our next lecture. But in ion implantation, we bombard the wafer with ions at a very high energy and embed those ions, dopant ions, into the wafer. One side effect is that we break up or bust up the crystal structure of the silicon. The result is we have an amorphous silicon material with our dopants in it. That's what the material looks like at the beginning of our annealing step, at the beginning of our diffusion step. Now, remember what we talked about interstitial impurities. They move around very quickly because they're not bound into the crystal lattice. Well, if we have amorphous material, then nothing is bound into the crystal lattice, and dopants diffuse very quickly in an amorphous material. Well, at the very beginning of the diffusion step, we have amorphous material, and therefore at the very beginning of the diffusion step, diffusion is very rapid. Now, pretty soon, the crystal structure will begin to grow from the single crystal base up through the amorphous material, and then we'll have dopants in single crystal material diffusing more slowly. But at the very beginning of the anneal step, the diffusion is rapid, and we call that transient enhanced diffusion. Transient means it only lasts for a little while. Enhanced means it's diffusing much faster at that very early stage of the anneal step. Another mechanism of diffusion is called interstitial C diffusion. Now, this is a little bit different than the diffusion of interstitials. Think of it like this. I've got a crystal lattice and it's full of silicon. But, especially at high temperatures where the crystal is not in its perfect form, we might have some silicons that are hanging out not in the crystal lattice. An impurity that's not in the crystal lattice is called an interstitial impurity. Well, if a silicon atom is in the mix but not in the crystal lattice, we call it a silicon self-interstitial. And self-interstitials move around very rapidly, just like impurities would if they're interstitial. So these silicons move around very rapidly, and then every now and then it might swap places with one of the crystal lattice atoms. That crystal lattice atom that it swapped places with is now an interstitial. Well, sometimes, every now and then, it will swap places with a dopant. So you have a dopant in the crystal lattice, an interstitial silicon moves around and displaces the dopant. Now the dopant is an interstitial. And that interstitial dopant can move very quickly before it displaces a different lattice atom and gets back into the crystal structure. That result is a faster or quicker diffusion than you get just from the other mechanisms like vacancy exchange. Now, another important issue involved with diffusion is oxidation. Now, often when you diffuse, you do these high temperature process steps, we get oxidation occurring. Maybe you want it, maybe you don't want it, but it often occurs either way. Sometimes, of course, we are purposely growing an oxide. If we grow an oxide on a doped silicon material, then that dopant will be diffusing while we're growing the oxide because it's a high temperature stem. What happens to the dopants? If I have a silicon interface, the oxide begins to grow, the oxide begins to take up some of the silicon, and interface moves down. What happens to the dopants that are in that silicon as the oxide grows? Well, it turns out that boron is very soluble in oxide. In fact, more soluble in the silicon dioxide than in silicon. But all of the N-type dopants, phosphorus, arsenic, antimony, they are less soluble in the oxide than in the dopant. The result is a redistribution of the dopant in the silicon just before the oxide interface. If you think about the N-type dopants, they don't like to be in the oxide. As the oxide interface grows down, it's going to push the dopants down into the silicon. And you'll get a layer just below the interface of the silicon and the silicon dioxide. You'll get a layer that has a higher than normal concentration of dopants. Basically, all the dopants that were in the part of the silicon that's now silicon dioxide have moved down into the silicon wafer itself. We describe the magnitude of this with something called the segregation coefficient. The segregation coefficient is M, is the concentration of the dopant in silicon divided by the concentration of the dopant in silicon dioxide. And for boron, the segregation coefficient is less than 1. It's in the 0.2 to 0.7 range, which means the oxide takes up the dopant, and just below the silicon dioxide interface, when we've done our oxidation, we'll have less boron than we had before because the silicon dioxide has taken it up. But for all of the N-type dopants, M is about 10. That is, the concentration of the dopant in the silicon dioxide will be 1/10 of what it was in the silicon, and the excess dopant will get pushed down into the top surface of that silicon wafer. Well, we're not done yet. There's another very important mechanism for diffusivity, and this is electric field enhancement of the diffusivity. Now remember, we put dopants into our wafer, but those dopants, once they find themselves in the crystal lattice, will ionize. They'll ionize into an ionized dopant and a mobile charge carrier. Well, the mobile charge carriers are mobile. And if there's a concentration gradient of dopants, there'll be a concentration gradient of charge carriers. These charge carriers will diffuse faster than the dopants because they're mobile. And when they do, they'll create a built-in voltage. Now, in the highly doped region, the resistivity of the material is very low. It's a good conductor because we have a lot of dopants. It's a good conductor. The voltage is going to be very small in those regions. But as we get closer and closer to the junction, where the resistivity of the semiconductor is higher and higher, any diffusion of the carriers will create a built-in voltage because of that higher resistance. Now, how does that voltage work? That voltage, the charge carrier moves faster than the dopant. The charge carrier is the opposite charge as the dopant, so it tends to attract the dopant. The electric field then pushes the ionized dopants in the direction of the charge carrier. This enhances their diffusion. So that's why we call it electric field enhancement of the diffusivity. Now this is true whether it's an N-type dopant or a P-type dopant. The charge carrier is always opposite in charge from the ionized dopant, and since it goes faster, moves further than the dopant, it tends to attract and pull the dopant along with it. We have an approximate equation that explains this. The enhanced diffusivity, the electric field enhanced diffusivity, is the diffusivity without electric field enhancement times 1 plus eta, this enhancement factor. This enhancement factor is approximately related to the concentration of the dopant at whatever position you're at, divided by the square root of c squared plus 4ni squared. So whenever c squared is bigger than ni, the intrinsic carrier concentration, then we get this enhancement. In a situation, for example, when C is much bigger than Ni, which happens a lot, then this term is negligible, the intrinsic carrier concentration, and we get eta of about equal to 1, and the diffusivity is enhanced by about a factor of 2. As the doping level goes down, this enhancement becomes less. What's the overall impact? We've got a lot of possible issues. We've got vacancy exchange, where the number of charged vacancies is a function of the amount of dopant. We've got electric field enhanced diffusivity. Both of these things tend to increase the diffusivity in the regions of higher concentration, and we get lower diffusivity in the regions of lower concentration. The impact can be seen in this graph. If I have a constant diffusivity, like shown here in the red, I have a dopant distribution that looks like a Gaussian. So on my log plot, it looks like a parabola. With a non-constant diffusivity, where the diffusivity is higher in the regions of high concentration, then I get a steeper gradient near the junction. So somewhere over here, there's going to be some background dose in the wafer, some background impurity level in the wafer of the opposite type as the dopant I'm adding, and we get a junction. So somewhere near the junction, which is maybe down in here, we see that it's a steeper profile than a constant diffusivity would predict. Well, knowing what that profile is quite important. So we tend to have models that predict this diffusivity, taking these mechanisms into account so that we can more accurately predict what this profile will look like. So let's talk about solving these kinds of diffusion problems. Well, last lecture we talked about analytic solutions. Well, analytical solutions are generally only available for the very simple case of constant diffusivity, not constant diffusion, but constant diffusivity, and very simple boundary conditions, like a few that we showed. For almost any other case, that is, for any real case, we have to use numerical solutions. And numerical solutions are generally implemented in process simulators that are now commercially available. A very popular process simulator out of Stanford is called Supreme. You can get it from Stanford, but you can also get it it's a commercially available variant. It's a 2D oxidation and diffusion model. Commercially, there's also three-dimensional 3D simulators available as well. And these simulators have many more complex models of how diffusion occurs than we can do in pencil and paper analytical types of solutions. So Supreme, very commonly used in the semiconductor industry. Now, one more thing I want to talk about when it comes to diffusion is the fact that diffusion doesn't just happen once. When I anneal right after an implant step. Any high temperature process step causes diffusion. And wafer processing involves many high temperature process steps. Oxidation, many depositions involve high temperatures. Lots of processing steps involve high temperatures. Every time I do an implant, I have to do a high temperature anneal step. For every one of these steps, there is diffusion. The more steps there are, the more diffusion there is. How do I take this into account? Recall when we talked about the various analytical solutions, one of them was the idea of a buried Gaussian. I put a Gaussian distribution of dopant inside the wafer. Then I let it diffuse, and we found out the result was another Gaussian. And this other Gaussian had a variance, a spread, that was equal to the original variance of the Gaussian plus the diffusion length squared. But we're going to use this idea to approximate the total effect of all the high temperature steps. For any high temperature step, we're going to have a diffusivity of the dopant and a time that diffusion occurs. So D is temperature dependent, and this is the time of that step. The square root of D times T is the diffusion length, so dt is the diffusion length squared. Now I'd have a second processing step. That dopant, that same dopant, has some other diffusivity at a different temperature probably, and it has a length of time T2. So at that second step, I have a second dt, and it adds to the first. And every high temperature process step after that, I simply add the dt's together. And the result is an effective dt, an effective diffusion length, an effective distance that the dopant moves from its original position to its final position for all of these different high temperature process steps. In general, the highest temperature process dominates because of the exponential nature of diffusivity with temperature. If I have one really high process step, a much higher temperature than the others, then chances are it will be that step that dominates. But if I have a whole bunch of process steps that are about the same temperature, then I have to keep track of all of these and add them together. And therefore it becomes critical to control the entire thermal budget of the process. From the moment I introduce a dopant, I have to keep track of all of the process steps that happen afterwards and think about where that dopant moves to when I'm done making the entire wafer, done with the whole process. If I've designed a process and then I decide at the last minute to add another high temperature process step at the end, I have to start from scratch. All of the design of the dopants and the diffusion steps took into account the total thermal budget of the entire process. And as soon as I add another one, that's all changed. And I have to go back and change my implants or some of my other process steps to accommodate this new high temperature process step. I have to design the process as a whole for the total amount of diffusion that will occur. So, goes to show you that process design is not the same as process step design. You have to design for the entire process. Last thing, let's talk about how we characterize diffused dopants. Now that we've got dopants in the wafer with some profile, some distribution of dopant from top to bottom or in depth through the wafer, how do we characterize those dopants? One way we've already talked about, CV curves. We saw that a p-n junction has a width and a capacitance that varies as a function of the bias voltage that we apply and the amount of doping on one side of that p-n junction, both sides of that p-n junction. But we can use CV curves to help us learn about the doping levels. We could also do sheet resistance measurements. Let me explain what sheet resistance is. We saw before that the resistance of a structure is the resistivity of the material times L over A. L is the length and A is the cross-sectional area. The resistivity, as we know, is a function of the amount of doping in a semiconductor. Well, let me take A, the cross-sectional area, and divide it and turn it into thickness times width. And then I'll have rho divided by T multiplied by L over W. Well, rho divided by T is what we call the sheet resistance. It's a function of the doping level, but also how thick the silicon is that is doped. In other words, rho over T says something about the amount of doping and its profile with depth into the silicon. L over W, on the other hand, is about the structure that we built. So if we build a sheet resistance measurement structure that looks like this, top down. So I'm looking top down on the wafer. I put one electrical probe here at the X and one electrical probe here at the X and measure the resistance. In this region, maybe these are metal pads here and here. In this region, I've got just my doped silicon. Maybe I've got oxide here and oxide here surrounding it. So I just have this narrow region of doped silicon. It's of length L and width W. And I can measure something about the sheet resistance of this region, which is the amount of doping and the depth that that doping occurs in, simply by measuring the resistance and then dividing by L over W. Well, L over W is an aspect ratio. It's the length divided by the width is sometimes described as the number of squares that that line has. So if I think about a square that is of width W, so a square might look like this, and then I ask how many of those squares can I fit along this line? Well, that's L over W. It's the number of squares. So if I measure the resistance and divide by the number of squares, I get the sheet resistance. So the units of sheet resistance is ohms per square. It's kind of a strange unit. Ohms per square is how we describe sheet resistance. We can also look at the profile of dopants by cross-sectioning a device, looking at it end-on and decorating or staining the dopant. We can have some chemicals that will react with the dopant so that in the doped region we see the stain, in the undoped region we don't, and then we make a measurement in a scanning electron microscope. That's SEM or SEM, scanning electron microscope. But by far the most important method, the most exact method for measuring dopant profiles is secondary ion mass spectroscopy, or SIMS. What we do here is in conception very simple. I take a beam of ions and drill a hole to
the silicon wafer. I'm doing ion beam etching. We'll talk about etching later, and you'll learn kind of exactly how this etching occurs. But basically, I send ions down, and it acts like a sandblaster to blast away bits of the silicon and drills a hole down. What I do is take the bits of silicon that are flying out and I put it through a mass spectrometer. The mass spectrometer measures the mass of the material coming out. So I can tell the difference between a silicon atom flying out and a dopant atom flying out. I count the ratio of silicon atoms to dopant atoms, and that tells me what the concentration of the dopant is. I do that as I'm drilling as a function of depth into the wafer, and now I have my doping profile, my concentration of dopant as a function of depth. This is a very important metrology method used to characterize doping profiles, and it's very commonly done obviously on test wafers, since we're drilling holes in our wafers, especially when we first set up our process, but also as checks every now and again. So that's our last lecture on diffusion. What have we learned so far? You should be able to easily answer these questions. If not, go back and review the material some more. How does charge in a vacancy affect diffusivity? Diffusivity of dopants, to be specific. What is the main cause of the concentration dependence of the diffusivity of dopants in silicon? Can you name two important causes of the concentration dependence of the diffusivity of dopants in silicon? Define transient enhanced diffusion. What is electric field enhanced diffusion? And finally, explain how the overall thermal budget for dopant diffusion is accounted for. Well, that's our lecture on diffusion. We perform these diffusion steps after ion implantation, and starting next lecture,
we'll begin describing the ion implantation process. Thank you.